a couple years ago, some of you may remember, I gave a talk on hacking voting systems. And it was while we were hacking the voting systems that we came across a question for which we just didn't have an answer. And the question is, if these voting systems are such crap, and they're so easy to exploit, everywhere you throw a dart, there's another exploitable vulnerability. Why is it that there hasn't been a single documented case of voter fraud because somebody has exploited one of these vulnerabilities? There isn't one case, and we looked. So we started thinking about this because this isn't right. It's not like US elections don't matter. It isn't like there's not a hell of a lot of money going into this. So if you had $100,000, would you pay for advertising or hire somebody to make the election go your way? And nobody's done it so far. So the only clue that we had, the only difference between a voting computer and any other type of computer is the fact that these systems are available to the public about 3 days a year. In other words, people haven't had time to learn them. So this makes a great hypothesis, but I'm a scientist. And you have to test a hypothesis. So what I'm going to talk to you about today are the results of my trying to test to see whether or not this works, or whether or not this hypothesis was actually correct. Now, I don't know how many of you write software or how many of you are software engineers, but the whole idea of software reliability, finding bugs and fixing bugs, has been at the center of software engineering pretty much since the field has began. The bug life cycle is highly predictable. This graph is from the mythical Man Month. And if you know anything about software engineering, this is the Bible. In 1975, when this book was published, Brooks came up with the idea that when you release a piece of software, it's got a lot of bugs in it. And some of those bugs are easy to find. And those easy to find bugs get found really, really early. And then you fix them, and then they get a little harder to find. And you fix those, and they get a little harder to find. And eventually, the curve gets pretty low, and at that point, you know your software is fairly reliable, right? Bugs are overwhelmingly discovered really immediately after the software is released, and then the curve drops, right? And this is remarkably stable over time. This graph is from 2008, which is 30 years after the publication of the mythical Man Month, and it shows exactly the same phenomenon. The actual numbers of bugs found were higher than Brooks predicted they would be, but the curve is exactly the same. So even if we can't fix the bugs, we do know that this aspect of software defects, this is well understood. But, you know, we're security people, right? We don't really care about bugs per se unless they become vulnerabilities that we can exploit. So here are some, just a list of some conventional wisdom, some assumptions that we all make. The first is that vulnerabilities are bugs, right? They just have really, really nasty side effects. The second really common assumption is that if we reuse software that's been out for a while, software that's been tested and has had a lot of its bugs removed, that makes the system more secure, right? It's new software that introduces new bugs. And the third assumption that we make is that if we can just improve the quality of our software, then we'll make it less vulnerable. If we can use the perfect type-safe programming language, and if we can find the perfect compiler, if we can just build those, then we'll have secure software, right? Well, no. This is what we found, that at least not in the early part of the life cycle of a product or a release of a product. This doesn't seem to apply. So here's what we did. We looked at a bunch of vulnerabilities, and we looked at just the early life cycle after each one. And in a nutshell, what we found is that there's this honeymoon period. It's immediately after release, software has this little bit of time that protects it. And this is going to have some really important implications that I'll discuss later on. So it actually looks like this. Instead of the way that the bug life cycle looks, with the curve starting high and then dropping down, the curve actually starts really low and speeds up. Low-hanging fruit or not, easy to find vulnerabilities or not, software seems to enjoy some sort of protection from attack in the time immediately following its release. And that's what we're calling the honeymoon effect. So now I'll get into a few of the details for you. This is what we did. We collected 30,000 vulnerabilities and correlated them with all the major vulnerability people, BugTrack, Secunia, NIST NVD, OWASP. And then we looked at a list of the most popular programs, whether they were operating systems or server apps or user apps, and we ended up with 700 different releases. Then all we did, no fancy statistical analysis at all. All we did was count the number of days. The number of days from the official release of a product or a version of a product to the days of its first vulnerability, its second vulnerability, its third vulnerability, and its fourth vulnerability. And that's when we discovered that at the earliest part, it seems to be safer here. So when I'm talking about a honeymoon period, this is what I mean. I mean that it's the time.
I can't see your laser pointer. Could you use a brighter one?
By the way, this is one of the co-authors of this work. This is Matt Blaze, professor at University of Pennsylvania. So the honeymoon period is that time from the initial release to the first vulnerability. But there was a rather high variance because different products, different developers release at different rates and fix at different rates. So in order to normalize the data, we use a ratio. We compare the release to the first vulnerability against the first vulnerability to the second. And if the time from release to V0 is greater than the time from V0 to V1, that's what we're calling a positive honeymoon. Okay? So I'm going to be using the term positive honeymoon and negative honeymoon a lot. If the honeymoon period is shorter than the time from V0 to V1, that's a negative honeymoon. Okay? Now, it's also important to realize that we're not comparing version 1 against version 1.5. We're only looking at the vulnerabilities within version 1 and comparing them against each other, and we're only looking at within version 1.5 against each other. Each release is looked at independently of the other. And this is important because of software quality issues. So here's what we discovered. In 62% of the releases we looked at, the honeymoons are positive. That means it takes longer to find the first vulnerability than it takes to find the second. This is exactly opposite of what is true for software reliability. And not only that, the time it takes to find that first vulnerability, the median number of days was 110. That's a long time. And not only does it take longer to find the first one to the second, but it is almost twice as long. The median overall honeymoon ratio is 1.54. That means it takes almost twice as long to find the first vulnerability as it does to find the second. Okay, so there's a honeymoon effect. Big deal, what does it mean? Well, at first we thought that this was a result of software getting better. There's absolutely no denying that things like secure design initiatives, the use of type-safe languages, fuzz testing, there's any number of things that make software that is written in 2010 of a much better quality than software that was written in 2001, right? So we broke it down by year. And this is what we found. It didn't matter. Doesn't matter what we look at, we have consistently positive honeymoons. And remember that our software reliability models tell us that we should find mostly negative honeymoons. We shouldn't find that there's 50% or greater positive honeymoons no matter how we look at it. So we broke it down every single way we could think of. We looked at just operating systems, consistently positive honeymoons. We looked at just server apps, same thing. User apps, same thing. We compared open source code to closed source code, and it didn't matter. It takes longer to find the first vulnerability than it takes to find the second vulnerability. So just for a second, let's consider the implications of this. The fact is, every software release is likely to enjoy a honeymoon from attack in the period immediately after it's released, even though not a single one of the bugs that it's ever going to have been fixed yet. This is contrary to our expectations based on what we know about bugs. We'd expect that the newly released software is at its weakest. Every single bug it's ever going to have, even the easy ones, even the low-hanging fruit, are still there. Yet it's precisely at this time, precisely when it's at its weakest, that it's least likely to have an exploit discovered. Okay, so this got us a bit confused. And we tried to figure out why. And what we discovered is this. Software has properties that are intrinsic to it and properties that are extrinsic to it. Intrinsic properties are the things that make a difference to software quality. They are how the initial product is designed, what type of language you choose to write it in. The skill of the programmer is important to the intrinsic properties of the software. But they're not important to whether or not it's vulnerable. That is related to the extrinsic properties, the things that the programmers and the developers themselves cannot control. And the extrinsic properties are legion. They're everything from the operating system it's running on, from the network interfaces, from what other applications or products are running on the system at the time. They have to do with the black market and the economics. What does a vulnerability for this particular product sell for? There's so many of them we don't know what they are, and we don't know how to measure them. But we do know that a lot of these extrinsic properties are growing at a rate faster that we can measure. Things are getting worse. So if most of these extrinsic properties were responsible for the honeymoon period, we'd see the honeymoon period drop to 0 because they are getting worse. But the honeymoon period is still consistently at 50% or greater. So most of the properties that are extrinsic to whether or not your software is going to be exploited don't matter to the honeymoon period at all. What does matter? We got our first clue when we compared major releases to minor releases. Major releases of a product are intended to sell a new product. They contain the most new features. They have the most new code. This is the primary difference because minor releases, excuse me, I need a drink. Minor releases are mostly bug fixes. And while they do occur with a lot more frequency than major releases, they don't have